Now, to analyze the solutions for the pure energy states in a potential like this, we know we go back to the time-independent Schrödinger equation. And it's actually the same time-independent Schrödinger equation that we've been solving all along when we looked at scattering states. So it has this general form, minus h bar squared on twice the mass times the second derivative of the wave function of this pure energy state, plus the potential times the pure energy state, gives me back then the eigenvalue, or the energy associated with that state, times then back the state again. And we have built up a whole toolbox on how to solve this equation, so we're just going to invoke that toolbox and find the overall solution. So the first step in doing this is to recognize that I now have three distinct regions, which I will number then 1, 2, and 3. And in each of these regions, we have different characteristic behaviors. I want you to notice that the behavior in regions 1 and 3 are going to be very similar because we have the same value for the potential. In both of these regions, these are classically forbidden regions because the energy is less than the potential. And therefore, we know that we have curvature in the solution, and the curvature is always going to be away from the x-axis. And the amount of curvature is going to be characterized then by an exponential constant, alpha. And that alpha then, we know the formula for it. It's the same formula we were using previously. We always have square root of 2m over h bar squared is the prefactor. It then multiplies, what goes in here is the difference between the potential and the energy, and the order we write it in is in an order so that we always get a nice positive number for taking our square root, because we've already accounted for which are imaginary or real by saying these are either exponential functions or oscillatory functions. So in this case, the potential is V at this level. The energy down here will be E, one of these values for E. So the difference then is V naught, to make it a positive number, which is higher, minus E. Now I would just like to comment that I'm just save on writing subscripts. I will just call this value alpha. Notice it has, of course, the same value in regions 1 and 3 because I have the same value for the potential. So I will just write a single alpha. Now, in region 2, that's our final remaining region, we have now a classically allowed region. The particle's allowed to be in there. In that case, I'm going to have curvature that is always going to be toward the x-axis. And that curvature is defined by another constant, k. The curvature constant in this case is the associated wave vector of the oscillations. It again follows my canonical formula. 2m over h bar squared times the difference between the energy and the potential. In this region, the potential is just 0, so that difference is just the energy, so it will be E. And that's my wave vector. And once again, I only have one region that has a wave vector associated with it, so I won't bother calling this k sub 2, and there's only one value then that I have to concern myself with. So this is the general situation. My job now is to begin to find the solutions to the time-independent Schrödinger equation in each of the three regions while I apply the appropriate boundary conditions.